You know, that internal energy and enthusiasm all the way up today. Your science teacher is right here to guide you through an energetic, one-shot explainer of chemical transformations, and we are going to do it without any fear. If you've ever found chemistry intimidating, just leave that at the door. We're going to break down the complex drama of elements coming together and breaking apart into clear, logical steps that make total sense.
So, here is our game plan for today. We are going to hit physical and chemical changes, equations and balancing, combination and decomposition, displacement reactions, and finally, redox reactions. Short, sweet, and to the point. Let's go.
Section 1. Physical and chemical changes. Before we get into the heavy stuff, we literally just have to ask ourselves, what exactly is a change in the physical world?
Well, think about physical changes. Melting a block of ice, or maybe tearing up a terrible report card you don't want anyone to see. You're just altering the state or shape of the object. Its internal formula stays exactly the same. Water is still water, right? But on the other hand, chemical changes, like the amazing smell of cooking food or the slow rusting of an old iron tool, they permanently transform the very composition of the material. The original substance becomes something entirely new.
Now, what's really fascinating is that sometimes both types of changes happen simultaneously. Take lighting a Diwali candle, for example. It creates both a physical and a chemical change at the exact same time. The melting of the solid wax into liquid, that is purely physical. But the actual burning of the wick, that involves combustion, it produces heat and light, which makes it a full-on chemical change.
Moving right along to Section 2, equations and balancing. Let's talk about the universal language of chemistry.
Now, I know balancing equations might seem kind of intimidating at first, but listen, if you just follow a few systematic steps to respect the law of conservation of mass, which just means mass cannot be created or destroyed, it becomes as simple as basic math. You just write down your elements, count the atoms in the reactants on the left side, and the products on the right side. Then you simply multiply with coefficients to equalize them, usually starting from the top of your list. See? It's just a logical puzzle.
All right, Section 3. Combination and decomposition. This is where we get into the real relationship drama of chemistry. How elements come together to build something and how they break apart.
First up, when two separate entities combine to make exactly one new compound, we call that a combination reaction. Imagine two people joining hands and moving into a single house together. In chemistry, two or more reactants merge to form one single product. Easy enough, right?
And you have likely seen a real-world combination reaction right at home, like when people whitewash walls. You start by mixing quicklime with water. This combination releases a massive amount of heat, making it an exothermic reaction, and forms slaked lime. Over a few days, this slaked lime on the walls slowly reacts with the carbon dioxide in the air to create calcium carbonate. This specific sequence is exactly why the walls of a house get that beautiful shiny white finish a couple of days after painting.
But conversely, when that chemical relationship breaks up, when one single reactant splits into multiple pieces, that is a decomposition reaction. However, relationships rarely break up on their own without some outside pressure. In chemistry, that means you need to add energy, usually in the form of heat, light, or electricity, to force that compound to break apart.
When we apply heat for thermal decomposition, color changes act as massive clues. Just like someone's face turns pale white when they get scared, those happy green ferrous sulfate crystals lose their water and turn white when heated, before finally breaking down completely into a reddish-brown iron oxide. Similarly, heating colorless lead nitrate breaks it down into a yellow powder, all while releasing these highly visible brown fumes of nitrogen dioxide.
We can also use electricity to break apart water, which is called electrolytic decomposition. We add a little acid to the water so it conducts electricity and then run a current right through it. To remember which gas goes to which rod, use the classic mnemonic trick CHOA, or Chalhat Oye. Cathode gets hydrogen and oxygen goes to the anode.
Okay, let's test your focus with a little sunlight magic trick. What do you think happens to a bowl of bright white silver chloride if you just leave it sitting out on a table in direct sunlight?
No way. It is not a miracle. It's photolytic decomposition. The energy from the sunlight actually breaks the compound apart. The white powder turns gray because the chlorine turns into a gas and escapes, leaving pure gray-silver behind. This exact light-sensitive reaction is the core science behind old-school black and white photography. It is also the exact reason why labs absolutely must store these specific chemicals in dark black bottles to stop the light from ruining them.
All right, Section 4, displacement reactions. Things are about to get highly competitive.
A displacement reaction is basically a chemical takeover. A more reactive, powerful element kicks out a weaker, less reactive element from its compound. Think of it as a powerful, wealthy guy coming into the picture and stealing someone's partner, leaving them all alone simply because the new guy was higher up on the reactivity ladder.
Now, to easily remember who is powerful enough to displace whom, just memorize this hilarious reactivity series trick. Katrina asked for a car, Alto, Zen, Ferrari, yet why did she get a silver Audi? The first letters map directly to the reactivity of metals from highest to lowest: potassium, sodium, calcium, magnesium, aluminum, zinc, iron, lead, hydrogen, copper, mercury, silver, and gold. If an element is higher on this list, it will absolutely displace anyone below it.
But in double displacement, nobody actually gets left alone. Instead of a hostile takeover, two different compounds just mutually exchange their ions. It is perfectly comparable to two rival sports fans swapping their team jerseys to keep the peace. Both elements swap their partners, forming two entirely new teams, or compounds, in the process.
And during these double displacement reactions, you'll frequently see a precipitate form. Basically, a precipitate is an insoluble solid that just suddenly appears and settles down at the bottom of the liquid after the reaction, kind of like dirt settling in a glass of water. A classic example is when you mix colorless barium chloride and colorless sodium sulfate, and boom, you instantly get a heavy, bright white precipitate.
Finally, Section 5, Redox Reactions. Let's tackle our last major concept for this explainer.
So oxidation, which is gaining oxygen, and reduction, which is losing oxygen, they are a total package deal. A redox reaction occurs when both take place simultaneously in the exact same reaction. It makes perfect sense, right? If one compound is losing its oxygen atoms, another compound in that very same mixture absolutely must be the one gaining them.
And to solve the trickiest part of redox, finding the agents, just use the swipe trick. First, write down the compound that gets oxidized and the one that gets reduced. Then, simply cross-swap their labels. The substance that gets oxidized is acting as the reducing agent, and the substance that gets reduced is acting as your oxidizing agent. Just swap them and you will get the right answer every single time.
Before we wrap up this explainer, I want to leave you with a bit of a provocative challenge. We learned earlier that in the electrolysis of water, the ratio of hydrogen gas to oxygen gas collected is 2:1 by volume. But think about their atomic weights for a second. What is their exact ratio by mass? Grab a pen, look at your atomic masses, and see if you can solve this mystery down in the comments. Keep that Josh meter high, and I'll see you in the next explainer.